So today we're going to look at a method called substitution that will help us integrate things that are too difficult to integrate without using it. And so when you're looking at using the substitution method, so you're going to get an integral, you're going to look at the integrand, it's going to look ugly, you're not going to know how to approach it. So that should clue you in that you're going to need this U-substitution. So you're going to look at part of that integrand, and you're going to look at, sometimes it's things that are in parentheses, it's what's underneath the radical, it's what's in the denominator, it's an exponent, but you're going to look at some piece as being your U value. And when you take the derivative of that, you're going to look at and see that there's a piece in that integrand that looks like what our derivative would be of what we chose U to be, so that things would like simplify out. Okay, so let me go through an example and I'll kind of explain what I just said again, but with an example. So for instance, let's say that we had the following. We had the integral, and this was of 2x times parentheses. So inside that parentheses, we have x squared plus 5, doesn't really matter. And end your parentheses, and that parentheses is raised to the -4 power dx. Okay, so we don't know how to integrate this. It has a negative exponent, so it's not like I can expand that out. I mean, I could put it in the denominator and expand it, but that would just make it even messier. Notice though, if we had what was inside this parentheses as a single variable, it would be easy to integrate. And also notice if you choose what's inside this integral to be your U value, so U is equal to x squared plus 5. When we take the derivative of both sides, notice this x squared plus 5 is going to have a 2x in it. Okay, so you're going to decide what U is going to be. Once you figure out what U is going to be, you're going to differentiate both sides. Of the U-substitution. And so if we differentiate both sides, so if we take the derivative of U, that's just 1, but we're going to tack on there that du. We just integrated, or we just took the, not antiderivative, not integrate. We just took the derivative of U. So now let's integrate x squared plus 5. So the derivative of x squared is just 2x. Derivative of 5 is 0. And we took this with respect to x on this side, so we're going to put on this dx. Okay, so if we go back in and substitute in, right now we have 2x. We have the parentheses, u, and that's all raised to the -4 power dx. So the problem here is that we still have u and x in here, and we're going to now be taking the antiderivative with respect to u instead of x. And so in order to take care of this, wherever you let u be and you took the derivative of both sides, you're always going to go back to that and you're going to solve for dx. So we want dx by itself, and so we could get dx by itself by dividing both sides by 2x. And so we get dx then is the same thing as du divided by 2x. So going back in, let's rewrite dx in terms of du. So we have 2x, we have u all raised to the -4 power, and then instead of dx, we're rewriting it as du all over 2x. So I can simplify this. We can simplify because we have a 2x in the numerator and denominator. And so now we're just integrating u to the negative 4th power du. Okay, so now it's in a simple form that we can take the antiderivative. And so taking the antiderivative of u to the negative 4, we're adding 1 to our exponent. So negative 4 plus 1 is negative 3. We're dividing by our new exponent of negative 3. This, notice, is an indefinite integral, so that's where we had to add our constant c. So once you've done that, we want to go back and substitute what you would let u be. So this is the same thing. We had chosen u to be, what was it? X squared plus 5. So we have the antiderivative, where the interval is x squared plus 5, all raised to the negative 3 power. All over negative 3 plus c. My original had a negative exponent, so I'm just going to leave it with a negative exponent there. If I had started originally with that in the denominator, I probably would rewrite that and bring that parentheses down and make the exponent positive. So sometimes when you're doing these, you might choose the wrong value for u. Sometimes it's just kind of trial and error and check. If you choose the wrong value for u, you're going to see that things don't cancel out nicely, and you're going to have your integrands with respect to x and u in there. I'm going to show you a case in a minute where we'll have to manipulate a little bit in order to get things just in terms of our u. But for now, let's look at a different case. So what if you had, well, these are actually what I was just telling you about. A lot of these are just what I was just telling you about. So maybe let's just pull one then. So what if you had, here's one. How about x all over the square root of 1 plus x dx? Okay, so looking at this, I don't know how to integrate it. I would look to see if this looked like one of my trig functions. I noticed that if I had a single term underneath this radical, I could maybe manipulate it where I could do some division. So let's choose our u value to be this 1 plus x. I also see that when I take the derivative of 1 plus x, I'm not left with an x in it, which worries me because that means something is not going to cancel. But let's just do it for now. So we have u, take the derivative of a u, that's 1 du, is equal to the derivative of 1 plus x. Derivative of 1 is 0, derivative of x is 1 dx. Okay, so dx is the same thing as du. So let's go back and substitute. We have x here, all over the square root, well, u was 1 plus x, and dx is du. Okay, but I also noticed that in here, so sometimes this is helpful. You want to go back to what you used u to be and solve for x in terms of u. So let's solve for x in terms of u. So I just want to get x by itself. So to do that, we're going to get x equals then u minus 1. Okay, so let's rewrite this. This is now the square root of x, but x is u minus 1 all over. I think we will be helpful if we rewrite this as u to the 1/2 power du. So now I have a single term in the denominator. So I could break this down as two separate fractions for my integrand. This is u over u to the 1/2. And this is minus 1 all over u to the 1/2 du. So I'm using my rules of exponents. Same base, which they are. I subtract. So 1 minus the exponent on the bottom 1/2 is 1/2. So I have u to the 1/2 minus, I don't like that u in the denominator, so I'm going to bring it up into the numerator by changing the sign of my exponent, so u to the negative 1/2 du. Okay, so we just manipulated something that we didn't know how to integrate using U-substitution. U-substitution, now we can integrate this. So now we can just use the general power rule where we add 1 to our exponent. So 1/2 plus 2/2, that's 3/2. Divided by 3/2, same thing as multiplying this by 2/3. Minus, add 1 to our exponent. So negative 1/2 plus 2/2 is 1/2. Divide by 1/2, which is the same thing as multiplying by the reciprocal of 2. And then we have to put in our plus c. Okay, so I'm just going to rewrite this. We had radicals in our original problem. We also need to rewrite what u was. U was equal to, is that x minus 1, right? No, it was 1 plus x. So we want to go back in wherever we see u, we want to substitute that with the 1 plus x. So we have 2 over 3, 2 in the denominator, that's a square root of 1 plus x cubed minus 2. So this right here, this is the square root of 1 plus x. And then we have our plus c. Okay, so we could always check this by going backwards, taking the derivative of this. We should get the original integrand, this x over the square root of 1 plus x. So let's say you had secant squared of 3x plus 2. dx. Okay, so I know what the derivative of secant squared u is, or secant squared x, but I don't know what it is with this 3x plus 2 in here. So if we choose u to equal 3x plus 2.
Is this another example?
Yeah, this is another example. So I got to figure out what U is so we can integrate. We know how to integrate, or hopefully we know how to integrate secant squared of U. So take the derivative of both sides. Derivative of U is 1, so du is equal to the derivative of 3x plus 2. So derivative of 3x is 3, and then we have dx. So if you divide both sides by 3, we get dx is the same thing as du all over 3. So this would be times dx, which is du over 3. So remember, you can pull our coefficient out front. So if we wanted to, this is the same thing as 1/3 secant squared of u du. So what do we take the derivative of and get back secant squared? Other than tangent x, oops, tangent u. So the derivative of tangent u is secant squared u plus c. So this is the same thing as 1/3 tangent, and u was 3x plus 2 plus c. And so what about dx all over x natural log of x? Okay, so there was we haven't talked about how to take the antiderivative of natural log of x. We don't know how to take the natural log derivative or antiderivative of natural log of x. If you have a natural log of x integram, that should be what you decide to choose u to be. So we're going to choose u to be just the natural log of x. Okay, so taking the derivative of both sides, derivative of u is 1 du is equal to the derivative of natural log of x. That was 1 over x dx. So we want to get dx by itself. And so we can do that. We can multiply x on both sides of our equation. So we get that dx is equal to x times du. So rewriting this, we have the integral of dx, which is x du, all over x times the natural log of x, but natural log of x is what we chose u to be. So notice things cancel and you just have this in terms of u. So the same thing as looking at the antiderivative or the integral of 1 over u du. So that was the special case. This was the antiderivative of 1 over u is the natural log, absolute value of u, plus c. Well, this is the natural log of what u was, but u was the natural log of x. Okay, so the antiderivative would be the natural log of x plus c. Let's look at an initial value problem. So remember when we were looking at the integrals and we were given values so we could figure out what C is? So this is similar to that. So let's say we have let's say we're given d squared s all over dt squared is equal to -4 times sine parentheses 2t minus pi halves. And we're given that s prime of 0 equals 100. And we're given that s of 0 is equal to 0. Solve the initial value problem. Okay, so this is kind of like an example. Remember, S, we were looking at sometimes denoted position of a particle at time t or object. Second derivative, or first derivative was velocity and second derivative was acceleration. So this is basically like they were giving us an acceleration of an object and wanting us to figure out the equation for the position function. And they gave us information about this right here. Okay, so we notice that we need to take the antiderivative of this piece to get the first derivative. And so I know that ds dt is equal to the integral of the second derivative. But the second derivative is just -4 sine of 2t minus pi halves dt. So looking at this, I don't know how to integrate it, sine of the 2t minus pi halves. So I notice that I know how to integrate sine of u. So let's choose u to be what's inside. So this 2t minus pi halves. Derivative of u is 1 du equals the derivative of 2t is 2. Derivative of pi halves is 0, so this is 2 dt. So get dt by itself, divide both sides by 2, we get du over 2. So ds dt is equal to the integral of -4 sine u all times du over 2. So notice that this 2 in my denominator is going to cancel out and leave this as a -2 in front of my sign. So we have ds dt is equal to the integral of -2 sine u du. Okay, so I know that the derivative and antiderivative of sine or cosine are the opposite of each other. One is positive, one is negative. I kind of have to think about it for a second. Let me bring down that -2. I know it's cosine. I don't know if it's positive or negative. Let me just think about it. So if I took, I want to get back, let's just think about it. I want to get back positive sine when I take the derivative. Cosine is going to give me a negative. So this is going to be negative cosine of u. Right, because if I take the derivative of negative cosine u, right? If I take the derivative of negative cosine u, the derivative of cosine u is negative sine times the negative out front. I should have to think about it, sorry. I have to also put that plus c. So we have ds dt equals this negative 2 cosine u plus c. So we have ds dt is equal to positive 2 cosine of u, but u was this 2t minus pi halves. Plus c. So that gave us enough information that we can figure out what c is. So initially, they told us that the derivative, first derivative of 0 was 100. So s prime of 0 equals 100. Right now we have s prime of t. Okay, so I know when I plug in 0 for t, s of t is 100. So I know I have 100 is equal to 2 cosine of 2 times, t is 0 there, 0, minus pi halves plus c. So I have 100 is equal to 2 times cosine of negative pi halves plus c. Okay, so thinking of your unit circle, negative pi halves, this is getting us, or we could think of odd or even functions too. But negative pi halves gets me here. Cosine on the negative y-axis is 0. And so I get 100 is equal to 2 times 0 plus c. So c is equal to 100. So we now have our first derivative function for our position. So s prime of t, this is equal to 2 cosine of 2t minus pi halves plus some constant, oops, plus 100. Found c was 100.
So are we plugging in 0 for t?
Yeah.
Okay.
They gave us s prime of 0, and t is this value number is representing t.
Okay, s prime 0. Okay.
So we want the original function. We want s of t, and we have the derivative. So s of t, my s does now look like integrals. S of t is equal to the integral of s prime of t, which is this 2 cosine of 2t minus pi halves plus 100 dt. Okay, so I want to break that down as to 2 separate integrals. I need to break this down as the first piece and the second piece. I notice if I don't break it down when I use U-Substitution, I guess I can still use U-Sub, and it won't give me too much problem. Okay, I guess we can do U-Sub. I did want to, that doesn't matter. U equals 2t minus pi halves. Du is equal to 2 dt. So dt is equal to du divided by 2. So this is equal to the integral of 2 cosine of u plus 100 And this whole thing is multiplied by du over 2. So notice this is like multiplying both of these terms in here by a half. And so if we multiply both terms by a half, well, 2 cosine of u times 1/2 is just cosine of u. And 100 times 1/2 is 50 du. Okay, so go through now and take the antiderivative of each piece. Antiderivative of cosine of u is sine u. Plus the antiderivative of 50 is 50u plus c. But sine of u was the 2t minus pi halves plus 50 all times 2t minus pi halves plus c. This is our original function s of t. I'm not done though. We need to find c. So I need to go back and look at the information they gave us, because for our initial value problem, I actually have it in front of me. They told us that s of 0 is 0. So this is saying when t equals 0, s of t is 0. So let's go back and plug in. So s of t is 0 is equal to sine of 2 times 0 minus pi halves plus 50 all times 2 times 0 minus pi halves plus c. Okay, so sine of negative pi halves. So same reasoning, if you look at your unit circle, that gets you down to the negative y-axis. Sine is your y value, and so that is negative 1. So we have 0 is equal to, this here is negative 1. And then we have plus 50 times, that goes away, negative pi halves plus c. So notice 2 goes into 50 25 times. I need to get c by itself, and so let's add the other pieces. So c is equal to, let's add 1 to both sides of the equation, 1. And let's add, this is really negative 25 pi. So let's add 25 pi to both sides. And so our original function is the sine of 2t minus pi halves I guess we could distribute the 50 now if we wanted. Might as well do that. So this is plus 100t minus 25, 50 times pi halves. So that's going to give me negative 25 pi.
Professor,
Yeah.
for C, shouldn't it be 1 minus 25 pi?
But I have that negative, right?
Yeah.
Right here, this minus.
Yeah.
C was positive, so I was adding this to the other side.
Oh, okay, okay.
And I was adding the 1 to the other side. So they were both positive.
Oh, okay.
So that's just 25 pi here, right? But then I had to add my C. And my C value is 1 plus 25 pi. So I actually noticed with me distributing that 50 in here, that things were going to cancel a little bit. Like notice my 25 pi here and my negative 25 pi plus a 25 pi, those go away. And so S of t then is equal to that sine of 2t minus pi halves plus 100t plus 1. Okay, so there's our initial value problem. So given the second derivative information so that we can figure out what C is, we could figure out what our original, gosh, that's way back there, isn't it? I don't know if you can read that. So basically, we can do definite integrals with U-substitution. You just have to be careful about the bounds. So now I'm just gonna, let's look at a quick problem. Let's say you had a definite integral, your bounds were from -1 to 1. You have 5r all over 4 plus r squared. And then that parentheses in the denominator is squared dr. Okay, so we want to choose a value for u. The thing is, when we do this, there's two different methods. We have to be careful with our definite integral and our bounds. So when we use U-substitution, we can change our bounds right away so that they're in terms of u instead of r. And to me, that's a lot easier. When I was a student, though, I liked it the other way. The other way is you can keep your bounds in terms of your original variable. The thing is, when you finish and you integrate, you have to go back and do the substitution of what you had chosen u to be. And then you would use these numbers. Where if we change our bounds right away, when we take the antiderivative, we don't have to go back and change our bounds later. Okay, so I will show you, I don't know if I'll have time to show you both ways, but let's just do the one. So let's do U-substitution. I can't integrate this, but I notice I can integrate something 1 over u squared. I also notice that when I take the derivative of the inside of the parentheses, it's going to have a 2r left, which is going to help me cancel with this r up here. So if I chose u to be 4 plus r squared, then du, the derivative of the other side, is just 2r dr. So rewriting this, dr, get dr by itself, is du divided by 2r. Okay, so now when I go back and substitute in, if you don't change these bounds, I want you to put in the variable that it represents. So this is r is -1, r is equal to 1. 5r all over, well, this is just u squared times dr, and dr is du over 2r. So what happened, I wanted it to happen and it did. Those r's are going to cancel. So now it's in a form that I know how to integrate. Notice that we have a coefficient of 5/2 here. If we want, we can pull that 5/2 out front. I have the integral, I'm not going to put my bounds on right now, of 1 over u squared du. Let's change the bounds on the integral to be in terms of u. Okay, so all you really have to do is plug in what you chose u to be, the r values on your bound, and solve for u. So if r was equal to 1, we'll plug it in here. We get 4 plus 1 squared. 4 plus 1, so u would have to be 5. So my upper bound is 5. Now plug in the lower bound, r equals -1. Ooh. What does that tell us? Any ideas? If we plug this r equals -1 here, and I get 4 plus -1 times -1, that's 4 plus 1, u is equal to 5. You remember there was a special rule. If you have the same bound on the top and the bottom, what would that give us? So we should get that this is equal to 0. Okay, let's do it the other method just to show that then. So the method without changing bound. Okay, so we had the integral, right, of r equals -1, r equals 1. And we had the 5/2 out front. And we had 1 over u squared. I'm going to rewrite that as u to the -2 power du. Okay, so integrate u to the -2 power, add 1 to our exponent. So this is u to the -1 power, divide by our new exponent, which is -1. This is 5/2. And this is r equals -1 to r equals 1. But u is equal to that, what was it, 4 plus r squared? So we need to go back in here and we need to replace what u was with that. So we have this 5/2. I'm going to pull the negative out front. So it's -5/2 all times 4 plus r squared to the -1. And we're going to look at this from -1 to 1. I guess I could bring this down to the denominator if I wanted. Does it help me? It doesn't really matter, does it? So we have -5/2. Well, this is going to give me 4 plus, plug in 1, wherever you see an r, 1 squared, which is 1, raised to the -1 power, minus, you're going to do the same thing here. You're going to plug in -1 wherever you see an r. So 4 plus -1 squared, all raised to the -1. Well, it's the same thing, right? This is the same thing as 1/5, 4 plus 1, Bring that down to the denominator, minus 1/5. So we get negative 5/2 times 0, which is 0. Okay, so either way, you're going to get the same result. I hadn't seen that before doing some problems like this in business calculus, where the bounds ended up being the same, and using that property, that knowing that if they're the same, you had to get back to 0. So I technically could have gone through the steps if I didn't see that those same bounds were the same bounds on my integral, and gone through the process and plugged in those numbers 5 to 5, and right away I'd see that that would cancel out. We're almost there. We're so close, guys, with what we need to finish. I know I didn't do very many problems. I only did one problem with substitution in the bounds with the definite integrals. So let me just pause the video or stop the video for the day and talk to you a little bit.